one of the first things we're going to do with these matrices is we're going to run into a concept called the determinant of the matrix. So a matrix is square if it has the same number of rows and columns. The two matrices you see at the bottom are 2 by 2 and 3 by 3. Those are both square as opposed to being rectangular. And every square matrix has an associated number to it that we call its determinant, that has geometric interpretations and formulas for it. And when we want to write it, we use vertical lines on either side of the matrix rather than using the usual notation for a matrix, which has square brackets on either side. So here's a 2 by 2 matrix. Its determinant is going to turn out to be 1 on the left, and here's another matrix on the right that's 3 by 3, and its determinant is going to turn out to be minus 18 if I didn't screw up the calculation. And each of these determinants has a specific method for calculating it. For a 2 by 2, this is fairly straightforward. You multiply the elements on the diagonal from upper left to lower right, and then you subtract the product of the two elements that you multiply from upper right to lower left. So a times d minus b times c. That's a formula we're going to be using kind of over and over, and it's worth remembering. So on the right hand side, I've drawn a little schematic of how you multiply those out. And the reason these 2 by 2 determinants are so useful is that they tell us actually about the area of parallelograms. If we think about these two columns as vectors, then we can use those two columns to build a parallelogram that has one pair of sides given by the vector AC and the other pair of sides given by the vector BD. And when you take this determinant, we actually get the area of that parallelogram, almost. We may not actually get the area. We may instead get minus the area. So depending on whether we get positive or negative, we learn something about not just the area of that parallelogram, but also the way the sides are oriented. So in this case, if the vector AC is actually within that parallelogram, goes counterclockwise to get to the next vector BD, then the sign is going to be positive. Where if it was the other side, if to get from this vector AC to get to BD you had to go clockwise, you would get a negative number as the 2 by 2 determinant. So they tell us about area and they tell us about orientation. 3 by 3 determinants are built from smaller determinants. So to calculate a 3 by 3 determinant, we have to kind of start with the top row, and we walk through the entries of the top row one by one. The entries are A, B, and C, and we multiply each three of those numbers by the determinant of the smaller matrix we get by leaving that row and column out. So A times the matrix we get by leaving row 1 and column 1 out, minus B times the matrix we get by leaving row 1 and column 2 out, and then plus C times the matrix we get by leaving row 1 and column 3 out. We alternate this way, positive, negative, positive. And there are more ways to calculate determinants than that. This is a particular one that pretty much always works for 3 by 3 matrices, and we don't need a lot of fancy methods because this isn't a class in abstract linear algebra. It's mostly concerned with 2D and 3D geometry, and most of the determinants we're going to be taking are 2 by 2 or 3 by 3. This formula has expansions and bigger versions that are handy. Some people might also have seen a version of 3 by 3 determinants where you add up all the ways that you can multiply together numbers along the diagonals, and you subtract all the ways that you can multiply numbers along the other diagonals. That formula is fine, whatever floats your boat. A 3 by 3 determinant has a similar interpretation to the 2 by 2 determinant in that it tells us now about volume. If we have 3 column vectors that make up a 3 by 3 matrix, we can put them together into a geometric shape called a parallelepiped, where we write down all the possible ways to attach these 3 vectors tip to tail to each other one by one, and those build a kind of rectangular prism or rhombus prism, or I don't know what the geometric shape should be called. The technical name for it is a parallelepiped. And when we calculate this determinant, it tells us about the volume. The volume of this resulting shape is the determinant of this 3 by 3 matrix. But it might be positive or negative, just like the 2 by 2. And just like with the 2 by 2, that tells us about orientation. In this case, because the first column is the green vector, the second column is the purple vector, and the third one is the blue vector, the sign is going to be positive or negative depending on whether those three vectors are a right-handed system, so green, purple, blue, or whether they're a left-handed system, green, purple, blue. If you can make your right hand fit to that list of three vectors like you can in this particular case, then it's going to be a right-handed coordinate system. In this example, because the first column is green, the second one's purple, and the third one's blue, you should check yourself that those do form a right-handed system, and this one is going to have a positive determinant as opposed to a negative